So we'll go ahead and get started. It's Wednesday, and we will begin chapter 9. And chapter 9 is all about kind of doing statistical inference, but this time we're going to be dealing with numeric variables. And so in chapter 7 and 8, we established the sampling distribution, the central limit theorem, and we did statistical inference based on that, where we created confidence intervals and performed hypothesis tests. And today we're going to continue doing statistical inference, but no longer with categorical variables, now with numeric variables. Okay, so we'll be taking a look at chapter 9, and we'll look at sections 1 through 4, and then next week we'll look at section 5, which is kind of a pretty big section in of itself. And so you have homework assigned, and then you'll also have a quiz this week due on Friday that covers the content from this week. So it'll be the second half of chapter 8 and chapter 9, the kind of the first 4 sections. All right, so an important idea is the sampling distribution. And the idea behind a sampling distribution is that whenever we select a sample, the people that we select that to be part of our sample are randomly selected. And so when you calculate a statistic based on a sample, your sample statistic is going to vary from one sample to another, right? So when we take a random sample of people and we say, what is the mean of these 30 people? And then we take another random sample of 30 people and we say, what's the mean, let's say the mean age of these 30 people? Because the people that are in each group are randomly selected, we're going to get different sample means. And so when we look at the sample mean and we look at it across many different samples, what we expect is the sample mean to be close to, but not necessarily exactly equal to, the population mean. So as we're calculating these things, we can calculate the sampling distribution. And so, we can expect some of the values of the sample mean to be more likely than some other values. And so here's kind of a diagram of maybe what your sampling distribution could look like. So the idea here is we have a big entity that we're going to call the population. And the population, again, is everyone who's relevant to answering your research question. But the idea is that the population is too big for us to observe directly. And so what we're doing is we're going to select samples, random samples from the population. And for each random sample, the size of the random sample is one value, n, okay? And all of the random samples we select are of size n. And each random sample has a different sample mean. For whatever reason, I used the symbol y bar. It's the same as x bar, except it uses the letter y. So from our first random sample, we get the mean, and it's y bar 1. And then from our second random sample, we get a mean, and it's y bar 2. Our third random sample, we get y bar 3. And from our fourth random sample, we get the mean, and it's y bar 4. And we continue doing this, and we keep selecting different random samples. And with every single random sample, we're going to calculate all of the different y bars that we observe, okay? And there's a little website that I can click, and this will kind of run a little applet, I guess, or a little demonstration that shows, how this could work, okay? So what I'm going to do here is this top histogram represents the sampling distribution not the sampling distribution, actually, the population. This top histogram represents the population distribution. This is everybody. This thing up here represents the big population over here. Okay, and so from this parent population, I'm going to start by taking, let's say samples of size 5. Okay. Okay, and so here is a random sample of 5 individuals taken from the population. And what you'll see is that every time I click this button, okay, it's going to draw kind of 5 individuals from the population. Most of the individuals that we see will kind of be in between here and here. Occasionally we'll get some values out here or even out here, okay? But very, very rarely, because there's hardly anyone in the population with a value of 32 or a value of 0, we will almost never see individuals selected way out here or way out here. It might happen, but it's going to be very, very rare. Okay, we might see a couple individuals selected close to the edge, okay, but very rarely at the edge itself. All right, so I'll just do this a couple more times. But overall, most of the values will be coming from this middle region. And every time I select a sample of 5, we're going to calculate the mean of those 5, and it's going to drop down kind of a little brick or a bar into this thing that says distribution of means. The distribution of means here is going to be what our sampling distribution is. It's going to be what we're doing when we keep track of all of the different Y bars that we see. Okay, so I'm doing this one at a time. A sample of 5, okay, and I calculate the mean of those 5, and the mean of the 5 kind of drops down. So here's another group of 5. We calculate the mean of those 5, and it drops down. So I can just repeat this, and we're going to continue taking random samples of 5. And so here's a sample where we've got a couple values that were a bit on the lower side, and so the average of those 5 end up down here. Okay. We keep getting values, again, mostly kind of in the middle-ish region, and we calculate the mean of those. Every now and then we get some values farther out, okay, but so far we haven't really seen any values all the way at the edges, okay? And so I can keep doing this, all right, each time taking a sample of 5 values and calculating the mean. And to just kind of speed things up, I can kind of, rather than having to see the individual samples, I can just click 5 here, and it will add kind of 5 bricks here. And it will kind of build up our sampling distribution, 5 at a time. All right. Now, one thing I want you to notice is the mean of the population is 16, okay? And this is our sampling distribution so far after 160 draws of samples of 5 each. And pay attention to what the mean is and what the standard deviation is. Okay, so the mean of the population is 16 with a standard deviation of 5. And I'm going to just keep building this up. And by taking more and more samples, the sampling distribution, this is kind of an empirical sampling distribution. The empirical distribution will end up looking closer to a theoretic distribution. So I'm going to go ahead, I'm going to go ahead and just click 10,000 here, or even 100,000. And so after close to, after a little over 200,000 random samples of 5, so it's this process where I'm taking random samples, and now I've done this not 4 times, but 200,000 times. Okay, now that I've done it 200,000 times, and we've kept track of every single Y bar, so I've got about 200,000 different Y bars or 200,000 different sample means that I've kept track of. Now I have the distribution of those sample means, the distribution of means, when my sample size is 5. And what we see is that it looks a lot like the normal distribution, okay? Its mean is 16, right around 16, so it's the same as the population mean. and its standard deviation is smaller. It's not a standard deviation of 5, which is the standard deviation of the population, but the standard deviation of this sampling distribution is around 2.24. Okay. Let me show you what would happen if I change the size of the sample. So if I go from n equal to 5 to n equal to 10, all right, when I click animate, it's going to draw a sample of 10 individuals from the population and take the mean, which it pops down right there. And again, here's another sample of 10. So in this sample, I did get, one value that was quite high up, not all the way up at 32, but quite high up. And even though this isn't maybe an unusual point, the average of all 10, because I've got kind of 9 that were still kind of from this middle-ish region, the average, even though I have one person who's got a really high value, the average is still kind of close to the middle. I'll do this again. Here's another sample of 10. The average of those 10 are right there. All right, so here's an individual where it's considerably lower than average. But again, when you average all of them, the piece that gets dropped down ends up kind of still in the middle-ish region here. Okay, so I think you guys get the idea. And I'm gonna go ahead and just start doing maybe 5 at a time. So we're collecting samples of 10, and we're doing 5 samples of 10, okay? And I'm building up my sampling distribution here. And I'll go ahead and just click kind of 10,000. So here we are. And so here we are after around 200,000 samples of size 10, okay? Again, this time I'm taking samples of size 10, and I've repeated this process 200,000 times. And what we get is that the mean of this thing is 16.01, so right around the mean of 16.0. And the standard deviation is even smaller. The parent population has a standard deviation of 5. And when we did samples of size 5, I think we got a standard deviation around 2.24. And then here, now we have a sampling distribution, our standard deviation of our sampling distribution is around 1.6, 1.59. Okay. And as I'm just going to kind of jump up. If I go up to samples of size 25, and I'll just animate this maybe once or twice, because it's the idea that I'm now drawing a big sample of size 25. So we get quite a variety of values here. And the mean of all 25 of those values ends up right here, okay? Oops. Let's do another sample of, say, 5. And, I'm getting a couple individuals kind of here on the low side here. But the average of all 25, because I've got also a lot in the middle, the average, even though I've got a few at quite low values, the average ends up kind of close to the middle anyway. Okay, and the average ends up there. And so again, I can kind of do 5 at a time. I'll go ahead and I'll just, here we are at around 200,000. We have a mean of 16 and a standard deviation of 1. Okay, and this is what it looks like. And so here's kind of a plot that shows what happens to our sampling distribution. So here's a sampling distribution when I took only samples of size 2. Here's when I took samples of size 5, size 10, size 16. And for each of these, what we see is that the mean all remains around 16, and the standard deviation continues to shrink from 5 to 3.5 to 2.24 to 1.59 to 1.24. All right. So I can run some code here, okay, to kind of do the same kind of thing, all right, except I'm not going to use the app here. I'm going to use R, and so okay, so let me actually clear this out. So the idea here is you can actually change the population from a normal distribution to, say, a uniform distribution, okay? With a uniform distribution, all the values are equally likely. So when we did normal distribution, only values near the middle were likely to appear. But with a uniform distribution, values on the edges are just as likely to appear as values in the middle. So we'll definitely see some values drawn from 0 or 32 or from these extreme sides. So I'm going to just do n equal to 10, and we'll take samples of size 10. And yeah, here we got a sample where 0 was drawn. And we're going to still take the average or the mean of all 10 of these values. Okay, and here's another sample of 10. Here's another sample of 10. Okay, here's another sample of 10, and this time we got a value at 32. And, oops. You can take, again, different samples of 10 and calculate the mean and plot it. And what might be surprising is that as I do this, the distribution ends up looking normal anyway. Okay, and so I wanted to kind of be able to explore this. If I take samples of size 2, what would end up happening? Okay, with samples of size 2, I'm just taking 2 values, and we're taking the average of those 2 values, right? So here's this plot. These 2 get selected, and we drop the mean right there, okay? These 2 get selected, and we drop the mean right there. Here's 2 that get selected, and we drop the mean. These 2 get selected, and we drop the mean. Those 2 get selected, and we drop the mean, okay? And so I can build this up, and we can see we're getting quite a bit of spread. And with samples of size 2, if I do a whole bunch of these things, if I do over 200,000, I get a distribution that looks like a pyramid, looks like a triangle, okay? But then if I jump up to samples of size 5 and I animate this, and I do, a couple 100,000 of these, now I get something that looks kind of like a normal distribution. And so in order to kind of, with the app, you only get to choose n equal to 2, 5, or 10. I want to kind of see what happens when we take samples of different sizes. And so here I'm creating a uniform population where the population has the values 0 through 32. Okay. And we're going to do 100,000 repetitions. And here I'm going to start off with sample size of 2. Okay. And you can see kind of the code that I run here, where I'm going to create a sampling distribution, right? And so I'm going to say for I in 1 through 10 to the 5, which is 100,000, okay, what we're going to do is we're going to use the function sample, which draws a random sample from the population. The population are the values 0 through 32 with replacement. Okay, so with replacement means we can select the same number again. How many values am I going to select? I'm going to select n, which is in this case 2. All right, so this will form a random sample of 2 values, and I'm going to take the mean of those 2 values and store it inside sample means I. Okay, and then at the end I'm going to create a histogram based on this. So I'll go ahead and do this, and indeed we get the same kind of plot that we saw, where we end up getting a triangle. Okay. And we can see what happens when I take samples of size 3. Okay, and now it's no longer a triangle, it's a little bit curved. It's not quite the normal distribution, but we're starting to get a little bit of curvature here in terms of area values near the middle are a little bit more common. So this is n equal to 2, and here is n equal to 3. Let me do sample means let's do this. I'll do n equal to 2. Run that with n equal to 2. I'm going to run this with n equal to 3. And then we'll try n equal to 4. Okay. And with sample size 5. So now it's getting, it starts to look more and more normal. Here it is with 6, 7. And at some point it's gonna, okay. So what we can see is that with 2, we start off kind of with this triangular pyramid looking thing. And then as I increase my sample size, we can see it starts to look more and more like the normal distribution. And we can also see the spread decrease, okay? And it is, you know, interesting to note. I mean, I could also do sample sizes of 1, okay? And again, with sample sizes of 1, we would get something that looks like the uniform distribution. This is just an artifact of the thing, but we're getting something that should look like the uniform distribution, okay? And so here's kind of a plot that summarizes it. You know, if I did the parent population is uniform, which is basically what we have here, when I take samples of size 2, I get this triangle, and I've kind of replicated that or duplicated that in R. And here it is with different sample sizes, 3, 4, 5, 6, 10, and 20. We can see at a certain point, it starts to look a lot like the normal distribution, okay? And as the sample size increases, the spread decreases as well. You know, what happens if we have something that's not normal at all, okay? Well, okay, I mean, the other one wasn't normal, but okay, so here is going to be a kind of a dichotomous distribution, okay? So in this thing, you can either get values that are very low or values that are very high, all right? And then you'll never get values kind of in this middle region, right? So what happens here? So here I can do samples of size 2, okay? And so you can see sometimes both values come from the top side, or both values come from the bottom, or maybe we get values from one from the top and one from the bottom side, okay? And I can keep animating this. All right, and And so what will the distribution look like when I create the sampling distribution? So, so this might be interesting, okay? After 100,000, I get kind of these three triangles, right? And what's happening is this triangle kind of represents, is basically this thing that's happening with the uniform distribution. We got a triangular distribution with an n equal to 2. And we're basically getting a triangular distribution for when both values come from the lower side. And same thing over here. We're getting kind of the triangular distribution when, from a uniform distribution where you select 2 and both values come from the upper side, okay? And then there are cases where the first comes from the lower and the second comes from the upper, and then the first comes from the upper side and the second comes from the lower side. So there's kind of twice as many ways to end up in the middle region, and we end up kind of getting another triangular distribution there, right? And I can kind of duplicate this in R as well, using a kind of redefining my population up here. Right. And so, with go ahead and just delete all of these out. Oops. So with n equal to 2, I run this, I end up getting kind of the three triangles, right? If I do sample size 3, okay, I end up getting kind of 4 triangles. This is all 3 came from the lower, 2 came from the lower and 1 came from the upper. 1 came from the lower and 2 came from the upper side, and then all 3 came from the upper, or the higher side of the distribution with n equal to 3. Here I'm going to bump it up to n equal to 4. All right, and now I get 5 kind of triangles with n equal to 5. I get 6 triangles, okay? And this is where all 5 came from the lower, all 5 came from the upper, 1 from the lower and 4 from the upper, 2 from the lower, 3 from the upper, 3 from the lower, 2 from the upper, 4 from the lower, 1 from the upper, and all 5 from the upper. I'm going to continue to increase this. And you'll notice that, we're still kind of getting this jagged distribution. There it is with 7. And then at some point, they're going to start to kind of merge into each other. All of these different peaks end up there it is with n equal to 11, n equal to 12, we get that. 13. So here, each time I'm taking larger and larger sample sizes, okay? So with sample sizes of 14, I probably have like 15 different peaks here, but they're all starting to kind of overlap and merge with each other, okay? With sample size of 15, you can still see a little bit of the artifacts of kind of maybe the jagged distribution, but things are starting to look, a lot more normal and a lot kind of smoother here, okay? 18, 19. Okay. So here at 24, I would say it looks quite like the normal distribution. Okay, and at 25, we get that 26, and so on and so forth. So if I scroll through all of the different sampling distributions, we can see here's kind of the evolution with n equal to 2, and as I kind of cycle through them, we can see the normal distribution emerge, which I think is rather surprising considering that the parent population looks nothing like the normal distribution, right? So this is what the parent population looks like with n equal to 2. And I can kind of just show, with n equal to 5, we get kind of 6 different groupings. With n equal to 10, we get, these weird peaks, 16, 20, and at 25, it all kind of merges anyway into a normal looking distribution. Again, similar kind of thing that we have here. It's just that with the web app, you can only select between 2, 5, 10, 16, 20, 25, and by running it in R, I can do all of these kind of values in between, and we can see the distribution evolve. Okay, so I think it's kind of neat that even though our parent population is this weirdly dichotomous population, when we take small samples, we're getting something that looks nothing like any other distribution we've seen. But then when I bump up the sample size to a very large value, we end up getting something that looks a lot like the normal distribution. Okay, and so here's I guess I even cranked it up to sample sizes of 50. Okay, and this looks a lot like the normal distribution. So if I just push this to 50 and I ran that, yeah, this definitely looks a lot like the normal distribution. Okay, so here's just kind of the results when we have a dichotomous population there. All right, so these were all just kind of demonstrations to illustrate basically the central limit theorem when it's applied to a numeric population. All right, and so the summary of this is that when we create a sampling distribution of sample means, so if we keep track of all the different sample means that we've created, which approximates our sampling distribution, what we find is that the mean of the sampling distribution, so when we ask what is the mean of this distribution of means, that's the mean of our sampling distribution, it ends up equal or at least very close to the mean of the population. Theoretically, this should be equal. This is not exactly equal. I get 15.99 versus 16.0. This is not exactly equal because this is technically an empirical distribution. It's based off of 200,000 simulation. It's not based off of the theoretic results. Theoretically, if I continue increasing this to say, like 1 million, then that number, the mean of your empirical distribution, should equal the mean of the parent population. All right, so this is, in theory, the mean of the sampling distribution should equal the mean of the population mean, or the population mean. The standard deviation of the sampling distribution shrinks as the sample size increases, and the standard error can be calculated using sigma divided by the square root of n, the population mean divided by the square root of n. And we saw that in our plots as n, when n was small, the spread was wide, the standard deviation is wide, the standard error is wide or large. And as n increased, that standard error kept shrinking and the amount of spread got lower and lower. And even when the population was not normal, we saw the same kind of phenomenon. As n got larger, our spread kept shrinking and shrinking. Even in our dichotomous population, this one will have the most amount of spread, and as we increase our sample size, the amount of spread shrinks and shrinks. And so this is kind of the perhaps, I don't know, for me it's kind of surprising or a neat result is that the shape of the sampling distribution becomes normal as long as the sample size is big enough. So even when your population looks nothing normal, looks totally crazy, is dichotomous or whatever it is, the shape of the sampling distribution ends up becoming normal as long as the sample size is big enough. And so this phenomenon is known as the central limit theorem. And we saw it when we did the proportions and we were dealing with a categorical variable, and we saw that you can approximate the binomial distribution with the normal distribution. That was the central limit theorem. And now we can say, we can also approximate sampling distributions of the mean with the normal distribution. So with categorical variables, the sampling distribution of P could be approximated with the normal distribution, and now we can say the sampling distribution of the means can also be approximated with the normal distribution. And so we still have the same kind of conditions to check. It's got to be, the sample has to be random and independently selected. The sample needs to be large enough, so it's the same condition, and the population needs to be big. This time when we check for the large sample, the way we check is a little bit different. And so if the population is normal, then any size sample is large enough. And we saw this when we did the sampling distributions. If the parent population is normal, I can take samples of size 2, and the resulting sampling distribution ends up being normal. So even though my sample is tiny, with samples of size 2 or samples of size 5, this distribution ends up being normal. But if the population is not normal, then larger sized samples are required. So the rule of thumb in general, a sample size of 25 is going to be considered large enough for most cases. So we kind of saw that also, even when I had the distribution that was very much not normal, okay, where it could only produce values between 0 and 5 or 27 and 32, and it couldn't produce any values between, say, 6 and 26, you know, that's a very strange distribution. Even when you couldn't do this, create values in between, the sampling distribution ends up looking normal. And the rule of thumb is the sample size of 25 is usually big enough, but if you have a very extreme distribution, something that's very skewed, all right, you might need sample sizes even greater than 25. And then the big population distribution condition is that if you're sampling without replacement, you want to make sure you're not taking a sample that's too big, that the population is at least 10 times bigger than the sample. So that's the central limit theorem. And so based on that, we can start answering some basic questions about random samples. All right. So here's just a simple example. So we're going to say when you measure people's pulse, okay, so you can measure the pulse rate of somebody, and we'll say the pulse rates of adult women in the United States are approximately normally distributed with a mean of 74 beats per minute and a standard deviation of 13 beats per minute. Okay, I kind of made up these numbers, so don't try to like double check with the American Heart Association or something. And so what we're going to do is we're going to select a random sample of 36 people. Okay, or a random sample of 36 women, and we're going to ask what is the probability that the mean pulse rate of the sample is under 71 beats per minute. Okay, so we're not asking about an individual. We're not asking what's the probability that one individual has a pulse rate under 71, but we're asking what's the probability that the entire sample, Okay, we're taking an entire sample of 36 people. What's the probability that that sample, the average of the sample, the mean of the sample, is under 71? So when we set it up, it's good to kind of just keep track of the information we have. So here we have n equal to 36. Our mean of the population is 74. So mu, which is the mean of the population, is 74. And the standard deviation of the population, okay, so this is of all the people, of all the women in the United States, standard deviation is 13. And we want to know what's the probability that the mean of our sample x bar is less than 71. So what we're going to do is we're going to use the central limit theorem to establish our sampling distribution. So according to the central limit theorem, I guess before we use the central limit theorem, we should check the conditions, all right? So is our condition, is the sample large enough? Is the large sample condition met? And here we said the population is normally distributed, so any size sample is large enough. We have a sample of size 36, so even if the population was not normal, the sample of size 36 is going to be considered big enough. The sample is randomly selected, and the population would be all women in the United States, all adult women in the United States, which is much bigger than 10 times our sample. Okay, according to the central limit theorem, we can say the sampling distribution of x bar comes from a normal distribution where the mean is equal to the population mean, which is 74, and the standard error is equal to the population standard deviation divided by the squared of n. So we're going to do 13 divided by 6, and we get 2.167. So our standard error is around 2.167 if we round off. And then, so we're going to find the z-score of the value that in question, which is, I'm getting a warning that my battery's running low. Plug that in. So our z-score is going to be 71 minus 74. Okay, so we take the value that we want to know about, which is what's the probability that x bar is less than 71. So we're going to do 71 minus the mean, 74, divided by our standard error, 2.167. I get a z-score of negative 1.38. And so now that I have a z-score of negative 1.38, I can go to the z-table to look up that probability. So I can go to negative 1.38. I get 0.0838 from our z-table, or I can plug that into R and ask for p-norm negative 1.38, and I get 0.0838, same answer. And so we're going to say our answer is that if we select a random sample of 36 adult women, there's around an 8% probability that the mean of our sample is going to be 71 or lower. Let me just take a moment to check in with you guys and make sure you guys are doing okay. So if this is all good, following me so far, go ahead and give me a little green check to let me know you guys are doing good. Let me also give you the first quiz answer for today. So your first quiz answer is the letter C as in cat or car. C as in cat is the first quiz answer. First quiz answer that for week 5, Wednesday. Okay. Great. All right. So let's see. Yeah, why don't we go ahead and take our first break right now? We'll take 5 minutes, and then when we come back from the break, we'll transition into doing our confidence intervals and hypothesis tests. So we'll take 5 minutes. So it's a little bit early, around 10:52, 53. We'll come back and do the rest of our chapter here. for the rest of the lecture. All right, so we left off, we established that the central limit theorem works for numeric variables as well as the categorical variables, which we saw in earlier chapters. And so now that we've established the central limit theorem for numeric variables, we can start doing statistical inference like the confidence interval, like the hypothesis test, and that's what we will do here. And so I'm going to kind of cover, you know, a fair amount at a decent clip here, and I'm hoping that because we've spent a lot of time talking about confidence intervals in previous chapters, and we spent a lot of time talking about hypothesis tests in previous lectures, that that all of this stuff will feel familiar and okay, even though, you know, a lot of the details on how you actually go through the calculations have changed. Conceptually, the big ideas and the concepts there remain the same. So let's go ahead and take a look at the confidence interval. So the idea, again, is that we create a confidence interval for the population parameter, in this case, the population mean, based on what we observe in a sample. And so this time we're observing a sample mean, and we're going to make a confidence interval for what we believe the mean of the population is. So, you know, right before the break, the kind of work that we've done was saying, you know, let's assume the population has this mean, and, you know, what's the probability of your sample looking like this? This time we're going to say we don't know what the population looks like, but I have my sample. The mean of my sample is this. Based on this value, what can I say about the mean of the population? So from the central limit theorem, we know that x bar follows a normal distribution, which means that in general, x bar, the mean of your sample, is going to stay close to the mean of the population. And so whenever we observe a sample mean, we can be confident that the population mean is close by. Or more specifically, we can be 95% confident that the population mean is approximately within approximately 2 standard errors of the sample mean. Right? Again, kind of the logic is that because we know the dog likes to stay close to its owner, whenever you see the dog, you can be confident that the owner is nearby. And similarly, from the central limit theorem, we know x bar stays close to the population mean. And so wherever we see x bar, we know that the population mean has to be close by. So kind of in a similar way that we created confidence intervals for the proportion when we were dealing with categorical variables, we can create confidence intervals for the mean, the population mean, based on your sample mean. And so we can say we're 95% confident that mu is between, and I'm going to do the mean of our sample, x bar, plus or minus 1.96 times my standard error, which is sigma divided by the square root of n. Right, and so this is where we are. However, there's an issue. There's an issue with setting up our confidence interval this way, and that is that this value, sigma, the standard deviation of the population, is unknown to us. Okay, if we knew what the standard deviation of the population is, then this is fine. But in general, and I can't think of any real life scenario where, because the whole idea of this confidence interval is that we don't know the properties or the parameters of the population. We don't know what the mean of the population is, and we're trying to create a confidence interval about it. And so I can't think of a situation where you don't know the mean of the population, but you do know the standard deviation of the population, which is what sigma is. And so we don't know what the standard deviation of the population is. And so what we're going to do is we're going to use the standard deviation of our sample's standard deviation, which is S. We're going to use that as our best available guess for what the standard deviation of the population is, right? So the standard deviation of the population is some spread, it's some value that we don't know what it is. And we're going to say, well, I don't know exactly what that is. And so just kind of as an estimate of it, I'm going to use the standard deviation of my sample. Because hopefully, The idea here is that your sample, because it was randomly selected, is somewhat representative of the population. Now, it might be, it might not be, but we're hoping that our sample is representative of our population, and therefore the standard deviation that I get from my sample is somewhat similar to the standard deviation of the population. So that's what we're going to use. We're going to use S instead of sigma, okay? But, so we're going to, oh, sorry. So when I plug that into the formula, the standard error of our sampling distribution is sigma over the square root of n, and we're going to estimate it, and we're going to say the standard error, estimated standard error, is going to be S divided by the square root of n. Okay. But the problem is that it's going to just add extra uncertainty. It's going to introduce extra uncertainty. This is a completely reasonable thing to do, right? If you don't know the exact value of something, it's reasonable to take an educated guess, right? So, so we have to do this quite a bit in life, in that you don't know exactly what the answer is. So you just take a reasonable guess, and right now, using S instead of, in the place of sigma, the standard deviation of your sample in place of the standard deviation of the population, it's a reasonable thing to do, but we have to kind of account for that extra uncertainty that it introduces. And so to compensate for this, what we're going to do is, rather than using 1.96, okay, we're going to just kind of fudge that number a little bit, okay? And it's going to be done via using the t distribution, right? So, so I wrote some stuff about this. I wrote, when we use S in place of sigma, we introduce some uncertainty. We don't know if our estimate S is going to be too big or too small compared to sigma. So sigma being the population standard error or standard deviation. And when you use S in place of it, because it's random, your S could be a little bit bigger than sigma, or it could also be a little bit smaller than sigma. Having an S that's too small is going to be problematic, because it's going to create a confidence interval that will end up being too narrow. And when you have and remember, when you make conclusions based off your confidence interval, you're going to be concluding based on whether some particular value is inside or outside of your interval. And so when your S is too small, you're basically casting a net that's a little bit too small, and you won't catch the value that you want. And so having an S that's too small could be a problem. And so what we're going to do is we compensate by intentionally fudging that number from 1.96 to something a little bit larger, okay? So we're going to make our confidence interval a tiny bit wider, and we're going to adjust the critical value to something a little bit bigger. So yeah, when we do a 95% confidence interval, instead of using 1.96, we're going to just make it a little bit bigger to something like 2.1, 2.2 or something. You know, we just kind of fudge this number a little bit, right? And so how much do we adjust? How much do we adjust? Do we go from 1.96 to 2.1? Do I go from 1.96 to 2.05? How much do I adjust? That's going to be based on something called the t distribution. The t distribution looks a lot like the normal distribution, but it's kind of intentionally just stretched out a little bit, okay? We say it has thicker tails than the normal distribution, in that we've kind of squashed it down and made the distribution a little bit wider. There's an interesting kind of history of the t distribution. Okay, so here's a question. Why didn't we do something like this when we substituted p with p hat, which is a great question. So the answer is a little, again, a little bit beyond the scope of our course, but when you substitute p hat with p with p hat, you are introducing some uncertainty. But it turns out that it kind of just balances out, and I guess asymptotically it doesn't really make a difference. So it did not, we did not need to compensate for this when we were substituting p with p hat. And I don't have a great answer right now, but it turned out the way p hat compares to p, the adjustment isn't necessary. But when you substitute s in place of sigma, it does. Okay, it's not a great answer, but that's kind of what happens here. So there's an interesting history of the t distribution. It was actually developed by a kind of a quality control engineer at Guinness Brewery. So Guinness Brewery in Ireland, you know, they make you know, Guinness beer. They're responsible for a couple things, right? You got the Guinness Book of World Records, which is kind of made to settle all of the arguments about extreme things when people get in arguments at the bar about like who is the strongest person ever or whatever. So they're responsible for the Guinness Book of World Records, and they're also responsible for the T distribution. But it was actually developed by this quality control engineer named William Gossett. He was trying to you know, run some, I guess, tests on, you know, these batches of beer, and based on his math, originally, you know, he would kind of reject things and say that, you know, we had to do a bigger, we have to redo the tests because, you know, he was working with smaller samples. But then they would come back and say, no, that's the wrong conclusion. And so he checked out the math and he realized, you know, he was basically using values from based on the normal distribution. He said, you know, I think I need to create a new distribution. And so he worked with a mathematician, came up with the T distribution. But then when he published it, Guinness Brewery didn't actually want their name associated with their employees' publications. And so he had to publish under a pseudonym, which he just said from a student, like a student of math or something. And so it's known as Student's T distribution, but William Gossett's actually the man. So anyway, the size of our sample is going to play a role in how much kind of compensation we use, okay? So if your sample is big, okay, if your sample is huge, you would expect your sample's estimate of sigma, that is your sample standard deviation S, to be a pretty good estimate of the population standard deviation, right? And so the amount of compensation you need to do is going to be just a little bit. You only need to compensate a little bit, and so you might use 1.99 instead of 1.96, only adjusting it by a small amount, okay? On the other hand, if your sample is small, okay, then your sample size, and then your standard deviation of your sample can't be expected to perform very well, as in it might be wildly different from the standard deviation of the population because you're basing the estimate based on a small sample. And so with a small sample, the value that we might use for a confidence interval might be something considerably bigger, like 2.365 instead of 1.96. Okay, so it might be considerably larger. And so this gets accounted for in something called the degrees of freedom, which we just call DF. And so when we're creating a confidence interval, the DF is going to be the size of our sample minus 1. So if you have a bigger sample, you have more degrees of freedom. If you have a smaller sample, you have fewer degrees of freedom. Conceptually, you know, degrees of freedom is actually an even deeper topic. I don't want to get into it, but for now, we're just going to say the degrees of freedom is going to be our sample size minus 1. So bigger samples will have more degrees of freedom, smaller samples will have fewer degrees of freedom, okay? And as the degrees of freedom approaches infinity, then what happens is the T distribution ends up matching the Z distribution. And so if you have a sample size that's huge, okay, something that's approaching infinity, you're going to end up using 1.96. You're going to end up using 1.96. And the rule of thumb is kind of like, if your sample size is over 50, just go ahead and use 1.96. Technically, it's still different. It's maybe like 1.99 versus 1.96, but the rule of thumb is, if you don't have a t-table handy and you've got a large z-score, if you have a large number of degrees of freedom, like 50 or more or something, you can just go ahead and use the normal distribution 1.96 value. Okay. Oh yeah, so this is about William Gossett, and you can watch these YouTube video clips about the t-distribution, but that's a side note there. All right, so this is what the t-distribution looks like. The t-distribution is available on CCLE under week 3. Under week 3, there is the reference tables. When I told you to download the reference tables for your z-table and t-table, well, so far we've only been using the z-table. The t-table is actually in the same file. So if you click the reference tables, you start off with the normal distribution. There's actually this binomial probabilities table, which you can kind of skip. And the last page is the t-distribution. It's in the same file. So if you're wondering where you get the t-table, it's available under week 3. So when you do your homework, you can do that. All right, and this is what the t-distribution looks like, okay? And so you'll notice at the top you have the confidence level at 95%. And then along the side you have degrees of freedom, okay? And so when the degrees of freedom is equal to infinity, meaning your sample size is infinitely large, you can use the values for the confidence interval are the same as the ones that we use for the normal distribution, which is going to be 1.96 for a 95% confidence interval. And you can see that as your degrees of freedom shrinks, meaning if you have a smaller sample size, the values that you're going to use get a lot larger than 1.96. So with a sample with 10 degrees of freedom, which would correspond to a sample size of 11, you use 2.228. Okay, and if you have a sample size of say 5, then you have 4 degrees of freedom, and you'd use 2.776. Okay, and you can also see kind of the other thing that so far I've been talking about 95% confidence interval, but the same ideas that we had for confidence intervals when we were talking about proportions applies here. And so when you have, if you want to increase your level of confidence, if you want to be more certain that the value, that the population parameter falls inside your interval, if you want to be more certain, you just have to make your interval wider, right? You got to cast kind of a larger net. And so when we were dealing with proportions, we said for 95% you use 1.96, and for 99% you use 2.58. The true values should be 2.576, it doesn't matter, but that number goes from 1.96 to 2.58, gets bigger. Same thing for if you had 10 degrees of freedom, so a sample size of 11, you go from 2.228 up to 3.169, okay? And if you want an even higher confidence level, in 99.8% confidence interval, you'd go even higher to say 4.144 or something. And again, on the other hand, if you want a narrower confidence interval, like if you want an interval that's smaller in size, which is going to generally more useful, the trade-off is you have to give up some confidence. You're going to be less confident in your response. So instead of 95%, you can be only 90% or 80% confident, and you can end up having a more narrow confidence interval. All right, and so this is all reflected in the t-table, which is available on CCLE in that one file there under week 3. Okay, so let's go ahead and put everything together. And so the confidence interval for the population mean mu based on a single sample is going to be this: x bar plus or minus t star times your standard error, which is s divided by the square root of n. And this part, t star times the standard error, is known as the margin of error. All right, and if you compare that to the confidence interval for P, it's P hat plus or minus Z star times P hat times 1 minus P hat over N. And you'll notice that both intervals are in the form of estimate plus or minus. So the estimate is either P hat or X bar plus or minus a critical value, which comes from a table, multiplied by the standard error. It's just the formulas have changed for the standard error, but the kind of conceptually, it's still the same. The question came in, says, what if you're trying to find a 97% confidence interval or something in between? Okay, so you don't have the values to do a 97% confidence interval, okay? I mean, you could try to guess and you can say, well, I guess the number I should use is somewhere in between here and here, but I wouldn't recommend it just because it's probably not going to be right. The other option is you could use R, and you can use a function called QT. So if you do QT, say 0.975 and 10 degrees of freedom, you know, here it gives me 2.228, which is this value here, 2.228 for 0.975. So if you wanted a 97% confidence interval, 97% confidence interval means you have 3% total on the outside. So half of that is 1.5%. And so you'd have 0.015 on one side and 0.985 on the other. So your confidence interval would be you'd use 0.985 and you'd get 0.527, okay? Again, that's beside the point. I'm not gonna ask about a 97% confidence interval, but I'm answering that just to answer your question there. So anyway, this is what our confidence interval looks like. We've got the estimate based on the sample plus or minus a critical value multiplied by the standard error. All right, so let's just do a silly confidence interval example here. And I don't know, I was brushing my dog the other day, and he's a Shiba Inu, and so he has an outer and he's got an undercoat. He's got kind of two types of fur anyway, so he's just shedding so much hair. And so I just thought, well, maybe the length of hairs on a dog's coat are normally distributed. I have no idea, right? So I'm just making up these numbers. And so we'll say we get a random sample of 10 hairs from the dog, okay? And you take you measure the length of each of these hairs, and it's 4.2 centimeters. Where is my dog? I think he's in the other room. I could show you pictures here. This is so silly, but I actually had a portrait of my dog painted here. Let me pause the recording. Okay. All right. So we'll say the mean length of the hairs, we'll say 4.2 centimeters, maybe a standard deviation of 2.2, so 2 millimeter standard deviation or something. We're going to make a 95% confidence interval for the mean length of hairs here. Okay, and so it's just a matter of plugging in the numbers that we have, right? So we got X bar, which is 4.2. When we look up T star in the table, okay, I have a sample size of 10, so I have 9 degrees of freedom. 9 degrees of freedom, 95% confidence, whoops, is going to be this number 2.262. 95% confidence, 9 degrees of freedom, 2.262. My standard deviation is 0.2. My sample size is 10. So I plug this in, and then you get 4.2 plus or minus 0.143. And my confidence interval ends up being 4.057 to 4.343. Okay. Question is, how does Z star differ from normal Z? Okay, so the regular Z is for your kind of normal distribution calculations, and Z star is going to be used only for confidence intervals. So when you created a confidence interval, I think I gave you guys a table in one of the lectures that just says for 95% use 1.96, for 90% use 1.645. And so those values in that table are known as Z star. They're known as the critical values from the table. And so it's not based on a Z-score. A Z-star is kind of just based on what the normal table says. And I think there's just 4 that you really need to know for the 90, 95, 99. I guess really only those 3. I mean, I think the table has for the 80% confidence interval, but I don't think I've ever seen an 80% confidence interval in life. So that's what we have. Oh, my dog is so cute. Thank you for saying that. I think he's cute too. Is it the same with T star? Yeah, so for T star, you have this table and you have these different confidence levels, and I'd say the most commonly used ones are 90, 95, and 99% confidence, okay? But yeah, I think because you have this table, I think it's reasonable. I don't think it's an unreasonable question to say, what is a 98% confidence interval? And because we have to take into account the size of our sample, the table is, has all of these different degrees of freedom to account for here. All right, and so the results of my confidence interval is, I say I'm 95% confident that the mean length of all hairs on the dog is between 4.05 centimeters and 4.343 centimeters. So basically, 4.05 and 4.35-ish, 3.34, okay? So these interpretations, I'm going to kind of go very quickly through them because I think you're all familiar with them. So if your confidence interval goes from here to here and somebody says, do we have evidence that mu is different from 4.0? We say yes, because 4.0 is not between the ends of our interval, right? So 4.0 is outside of the interval. So we say we have evidence that mu is different from 4.0. Do we have evidence that mu is different from 4.1? Okay, and the answer here is no, because 4.1 is inside of my interval. This is considered a plausible value, and we would say we don't have evidence, we do not have evidence that mu is different from 4.1. Do we have evidence that mu is equal to, say, 4.2? All right, and the answer is no. Okay, the confidence interval will never provide evidence that the parameter, in our case mu, is equal to some exact value. So even though it's inside the interval, we can't say that we have evidence that it is equal to 4.2. So I'm hoping this is familiar, and because these are pretty much the exact same conclusions that we made when we were talking about proportions. It's just that rather than talking about do we have evidence that P, the proportion, is equal to some percentage or some proportion, now we're talking about the mean of the population is equal or not equal to, or is different from some numeric measure. Is that feeling good? Everyone feel okay so far? Let me go ahead and give you your second quiz answer. Second quiz answer is D as in dog, okay? D is your second quiz answer. D. Okay, all right, and so now we'll talk about a hypothesis test, okay? So I hope, again, I'm gonna go work through this kind of quickly, but I hope it feels okay. So here's just a silly example. We're gonna say, we're gonna ask the question, is the average length of a banana 7.5 inches? I don't know, I just bought some bananas the other day. Oh, I'm gonna make a mess here. But if you measure how long the banana is, I don't know, okay. Second quiz answer, just to repeat, is D as in dog, D as in dog. It's the second quiz answer. All right, is the average length of a banana 7.5 inches? I have no idea, okay? So let's say you go to the grocery store and you somehow get a random sample of 20 bananas, okay? Or actually, you can't go to the grocery store to do this because I don't know. I don't even know if this is even possible in real life. But somehow we get a sample of bananas. We're gonna assume that it's random, which maybe is not even possible, but we're gonna measure the lengths of the bananas, okay? So we measure these. We'll say the average length is 7 inches with a standard deviation of 0.7 inches, okay? So does this provide evidence that the average length of a banana is not 7.5 inches? All right, so we wanna know, do we have evidence that the mean is different from 7.5 inches? Okay, I don't know. All right, so when we took a sample, the mean is 7. With this standard deviation is a sample of 20 bananas. All right, so we're gonna set up our hypotheses. When we deal with hypotheses, okay, when we create hypotheses, they're always about the population, all right? So when you're creating hypotheses for hypothesis test, when you're dealing with proportions, it was always about the population proportion P, not the sample proportion P hat. And similarly, when we're dealing with making hypotheses for a numeric variable, it's about the population mean mu, and it's never about the sample mean x bar. All right, so we always are going to write mu is equal to something versus mu not equal, or mu greater than, or mu less than. So in our case, because it said the average length is different or is not 7.5 inches, we're going to say mu is not equal to 7.5 for the alternative, right? If the question had, do we have evidence that the mean is less than 7.5 inches? Then we would say mu is less than 7.5, okay? Null hypothesis always has an equal sign. And when we're dealing with numeric variables, it will always be about mu, never about x bar. So we're going to go ahead and pick a significance level. We'll default to 5%. We can check the conditions. I'll just go ahead and tell you that the conditions are met, all right? We took random sample of 20 bananas. In real life, I don't know if you can actually get a random sample of bananas. You just have to kind of assume that when you go to the grocery store, maybe they're random, but that's probably not a good assumption because, well, I don't know. Who produces all the bananas? Chiquita and Dole? I don't know. Those are probably your big banana producers. And I don't know. I don't know if they are representative when you go to the store. So anyway, large sample condition. We took a sample of size 20, okay? Which, if the distribution of banana lengths in the population is unimodal and symmetric, sample size of 20 is probably big enough. But if it's really skewed or something, it's possible that it's still not big enough. The rule of thumb is 25, and our sample is a little bit shy of that. So this condition may or may not be met. So you might want to note that, okay? But we'll kind of assume that it's met, and we're going to just keep going from there. And the population would be all bananas, and that's going to be a big population. I don't know how many bananas there are in the world, but there's a lot. Okay, it's a lot more than 20 times 10. So the big population is met. All right, so the p-value, like all of the other hypothesis tests, is what is the probability of observing our data or something more unusual if the null hypothesis were true. All right, so if the null hypothesis were true, then the mean of the population is 7.5. That's what we've written in the null hypothesis, okay? And in our sample, we got a mean of 7.0, right? We have a sample of 20 bananas, and the mean of our sample is 7.0, and we want to know what's the probability of getting this sample, observing our data, or something more unusual, okay? So we got 7.0, so something more unusual would be 7.0 or less, and because it's a not equal sign, we're also going to check 8.0, okay, because this is 0.5 away from the mean. So we're going to go 0.5 below and 0.5 above, which would take me up to 8.0. So we're going to go 8.0 or something more extreme. So we're going to look at 7.0 or less, 8.0 or more, And that's going to be kind of, we want to know what's the probability of getting something like our data or something more unusual. So if the null hypothesis were true, the population mean is 7.5, and we expect random samples to be close to 7.5, and we got 7.0. So we're going to ask, what's the probability of getting a sample with x bar less than or equal to 7.0, or x bar greater than or equal to 8.0? And so, based on the central limit theorem, we know that the sampling distribution of x bar can be approximated with a normal distribution. Right? And so we're going to say x bar comes from a normal distribution with mean 7.5 and standard error equal to 0.1565. Right? But again, the problem is that we don't know the standard deviation of our population. So this is actually the estimated standard error. The estimated standard error is S divided by the square root of n. And so because we're estimating the standard error, instead of the normal distribution, we're actually going to have to use the t distribution. All right, and that's because, so the central limit theorem says it can be approximated with the normal, but again, because we're estimating our standard error, we're going to have to use the t distribution to get our p-values. All right, and so this is probably the, maybe the next part is going to be the part that feels a little bit strangest here, okay? So I'm going to get a test statistic, and I'm going to call it t. We calculated the same way we find a z-score, but we're going to call it t because we're going to use the t distribution instead of the normal distribution. So we find our test statistic the same way we find a z-score. We do x bar, the value that we've observed, 7.0, minus the mean from that we expect in our sampling distribution, which is 7.5. That's our population mean. And we're going to divide by our standard error. And I get a t-score of negative 3.19. And what I'm going to do is I'm going to look this up in the t-table, and I'm going to use 19 degrees of freedom because I have n minus 1 degrees of freedom. I have a sample size of 20. 20 minus 1 is 19 degrees of freedom. So I'm going to go to the t-table, look at 19 degrees of freedom, and we're going to try to find this value, negative 3.19. Okay? So using the t-table is very different from using the normal table. So this is going to take a little bit of getting used to. All right, and so what I've done is I've just kind of taken this row, all right? So these are the headings up here, and I've just kind of isolated this row with 19 degrees of freedom. So it's 1.328, 1.729, okay? So this row with 19 degrees of freedom shows up right here, all right? And our test statistic is negative 3.19. And so the way it works is you say, well, where would 3.19 fit in this row of numbers? Okay, so 3.19 is in between 2.861 and 3.579. Okay, I know our test statistic is negative 3.19, but the t distribution is symmetric. So right here it says right tail probability, but and all the values are positive, but because it's symmetric, I could also have the flip side where it's showing the negative side, and it would be equivalent, okay? So I have a couple pictures here. It's not the pictures I want. Huh, okay, I will have to draw this then. So this number 3.19 fits in between 2.861 and 3.579. And so what that means is that the corresponding tail area Okay, right here it says the right tail probability. Okay, the corresponding tail area is going to be in between 0.005 and 0.001. Right. The alternative hypothesis is two-sided, so our total p-value is going to be 2 times our tail area. Let me just show you what's happening here. So let me pull up. All right, so this is supposed to be my t distribution. All right, and all right, and so the idea here is I've got, I put 0 here, and technically we're at negative 3.19, but it's symmetric, so whatever answer I get is going to be the same as positive 3.19. Okay, and the idea here with this table here is that if and this is very exaggerated, but if I draw a line at say 2.861 and I shade everything to the right, the total area to the right is going to be equal to 0.005. That's what t.005 is, okay? And if I go further away, oops, what just happened here? I don't want this. Okay, if I go further away at from 2.861 to 3.579, at 3.579, the area in my tail here is going to be 0.001. Okay, that's what these numbers mean. And so here I am at 3.19, and at 3.19, I don't know exactly how much I have in the tail. I do know that my tail area is going to be more than 0.001 and less than 0.005. So my tail area, whatever it is going to be between these two values, between 0.001 and 0.005. I don't have an exact value. All I know is that according to our table, if it was at 2.861 exactly, I would have 0.005 exactly. If it was at 3.579 exactly, I would have 0.001 exactly. But here I have 3.19, so my tail area is somewhere between 0.001 and 0.005, right? Here's a question. What if my t came back as, what if t was, say, 4.2? What is my tail area? What can I say about my tail area? All right. So if t were 4.2, let's say I put in right here, 4.2, okay? I don't know, the answer is I don't know the exact tail area, but I do know the tail area, whatever it is, tail area must be less than 0.001. Does that make sense? Because I'm even farther away from 0. It's more extreme, and so the tail area is kind of how much goes beyond the critical value here, how much is beyond this number, 4.2. And we know that the area beyond 3.579 is 0.001, and I'm even farther away from 0, which means the amount left over here has to be even less than 0.001. So I don't know exactly what it is, but I do know whatever it has to be less than 0.001, okay? All right, yeah, the question is there a way to find the p-value using R? Yes, there is, okay? And you use, the function is known as pt, okay? Now, R always gives you the area to the left, okay? So if I do pt and I type in 2.861 with 19 degrees of freedom, it's going to say the area to the left is 0.995. So you can get the area to the right by doing 1 minus pt 2.861 with 19 degrees of freedom, and you get basically 0.005. And if I type in 3.579, 1 minus pt of 3.579, I'm going to get 0.001, okay? 0.001, you know, pretty much 0.001, okay? And so if I do 3.19, which is our t value, okay, 1 minus pt of 3.19, I'm going to get something in between 0.001 and 0.005. And so the exact value is 0.0024, 0.0024, okay? And if I type in pt 4.2, then I'm going to get a value, some value less than 0.001, okay? I get 0.0002, okay? So you can do all of this in R, but you don't need R. You don't need R. You can use the table and you can answer the questions. Because we don't actually need to know the exact p-value. We just really need to know if the p-value is going to be bigger or less than our significance level. So with a significance level of 5%, we really just have to see is our p-value going to be more or less than that. So whatever our answer is, okay, we know that the tail area is between 0.005 and 0.001. Okay, we know our tail area is between those two numbers. And because my alternative is a two-sided test, I had a not equal sign, and the alternative, I'm going to double my tail area to get my p-value. And so my p-value is going to be between 2 times 0.005 and 2 times 0.001. So my p-value is between 0.01 and 0.002. And again, I don't know the exact p-value unless I use R. Okay, with R, I can get the exact p-value, and I can say it's exactly 0.0024. And I would take that number and I multiply it by 2. And I would compare this to my alpha. If my significance level, my alpha is 5%, I know my p-value, because it's between 0.01 and something even smaller, 0.002, I know my p-value is less than alpha, and I would reject the null hypothesis. And so the conclusion would be, so while getting a sample mean of 7.0 inches is possible, we would consider it to be unlikely to happen if the population mean is 7.5 inches. So the fact that we observed a sample with a mean of 7.0 inches indicates to us that the claim that the mean banana length of 7.5 inches is wrong, and therefore we reject the null hypothesis. We conclude that the mean banana length is some other value, you know, maybe 7.1 or 7.2 or 6.8 or something, that would more easily produce a sample that has a mean of 7.0 inches. All right. Do we have any questions? This is technically the last slide I have in today's lecture. You have a couple exercises like this in the homework. You know, make sure you do your reading for chapter 9, and you can expect to see a kind of a t-test in this week's quiz. So you got quiz 4, and you'll see, you know, the 2 proportion test and the hypothesis test for a t-test using 1 sample mean. Because the t-test is new and kind of following the steps, you know, while similar to the other things, it is also different, and using the table is different enough that it causes, you know, trips some students up. So I just kind of want to warn you And, I guess in the last time I taught this class, people's quiz 4 grade, was probably their lowest of the 4 quizzes. Not by much, okay? Like the average was just a little bit lower. And I also want to just remind you that the quizzes are intended to be low stakes opportunities for learning. So if you mess up quiz 4, it's not a huge deal. Each quiz is worth a total of 3 percentage points. And so even if you like totally mess it up and you get like a 50% on your quiz 4, and I don't think that's going to happen to many of you. Okay, but even if that were to happen, 50% on a 3-point quiz is like 1.5 percentage points at the end of the day. So it's not a huge deal. So if you feel like, oh, I didn't do so great on quiz 4, don't worry. Okay, take that as a learning opportunity to prepare you for the final, which is coming up next week. It seems so crazy, but take it as a learning opportunity. Don't beat yourself up over it. It's just a quiz. All right. Oh, last quiz answer for today. The last quiz answer for today is A as in apple. A as in apple. A question. How do we know when to find Z or T for the test statistic? Okay, Z is for proportions and T will be for means. So that's going to be kind of the guideline. So if you're dealing with proportions, you're going to be using a Z test. If you're dealing with means and a numeric variable, you're going to use a T test. Will the reading be in the quiz? I don't think there's anything in the quiz that I haven't covered in the lecture. All right, so you should still do your reading of the book and the homework problems and all of that, but I don't think there's anything that is covered in the reading that there's nothing in the quiz that I wouldn't have at least spoken to in lecture. So again, the last quiz answer is A as in apple. Let's see. And then does the final cover most chapters evenly, as they're more heavily focused? Definitely more heavily focused on the last 3 chapters. So the final exam will be very heavy on stuff from after the midterm, chapters 7, 8, and 9. I would say even heavier on chapters 8 and 9 with, some stuff from chapter 7. Okay. Oh, I'm sorry. The article that you had to read. Okay, no, the article that you had to read is not going to be on this week's quiz. There will be a few questions regarding the journal article on the final exam. Okay, so for the journal article, there will be probably like 2 questions on the final exam about it. Yeah, but I don't have anything about the journal article on this week's quiz. Should you still review chapters 1 through 6 for the final? I don't know how to answer that question. So everything kind of builds on each other in that, like, if you didn't understand how to use the normal table from like chapter 6, and if you don't know how to like handle standard deviations from chapter 3, then you're going to be in trouble for chapters 7, 8, and 9. However, but do you mean like, will I have questions that are like oddly specific to chapter like 4 or something? Probably not. I don't know. It's a little strange because the concepts are cumulative in that you won't understand chapters 8, 7, 8, and 9 without understanding the earlier chapters. Do I have questions that are like specific? Generally not a ton. So I've got most of the questions are going to be from chapters 8 and 9 and chapter 7, 8, and 9, I should say. There might be a few definition-based questions that come from chapters 1 through 6. So I guess in that regard, you should still review a little bit. What sections should we review for the Gradescope quiz? So for this week's Gradescope quiz will be the stuff I've covered in lecture. So it'll be the second half of chapter 8. So that's going to be basically the hypothesis test for comparing 2 proportions. hypothesis test for comparing two proportions, and what we covered today, which will be the hypothesis test or the confidence interval for a mean from a numeric variable. Okay, and a question, how bad does missing a lab from last week affect your grade? So labs are worth 2 percentage points each, and quizzes are worth 3 percentage points each, and so so you know you'll have to figure out how much that affects you. You know, some people feel like the only acceptable grade is an A, and so losing 2 percentage points is a big deal, because you know, to make an A, you got to get at least a 93% in the class. So that's an A even, and to them an A minus is unacceptable because, you know, you're going for that 4.0. And so, you know, everybody has different kind of standards for what grades are acceptable and unacceptable. So a loss of 2 percentage points in a lab is gonna mean different things to different people depending on what is an acceptable or unacceptable grade. So some people are just looking to pass this class with a C, which is a 70%, and they just need to get it done to get at it, you know, get their graduation and get their degree and go. And so losing 2 percentage points, not that big of a deal. So other people want to go on to medical school or whatever it is, they need to get, or law school or something, and they need an A, they really want that A. So anything less than 93% is unacceptable. So a loss of 2 percentage points is different. So I don't know how to answer that question. Okay, will the final be longer than the midterm? You'll have the same amount of time. Number of questions, I don't know. They're designed to be for the same amount of time. I think I have it the appropriate length. I've taught this class enough times where I feel like I've made enough adjustments to the final where it's a reasonable exam. So I think the length of the final is appropriate based on, you know, every time I teach the class, I kind of look at the exam scores and the distribution to see if I need to make tweaks to the tests and exams, and it's at a fairly good place for what I feel comfortable with. So. Okay, so anyway, I hope that answers all of your questions. So we'll end here. Have a good weekend. Good luck with your, I guess, your last quiz for the week. I'll have office hours on Friday, and we'll see you guys next week. And maybe next time I'll just remind me, I guess on Monday or whatever. No, well, not, I guess Monday's the holiday. Okay. Oh, so have an extra. Enjoy your holiday, although I will be lecturing again. I'll be lecturing on Monday, but I'll record the video and you watch it whenever you want to watch it. Okay, enjoy your weekend, and we'll see you guys, I guess, whenever we see you guys next.